It's recording. So here we go. Right, we're doing an exam paper of some sort. It is, I've written on it, it's summer 2013, M1. And here we go with question 1, with the coolest AS Further Maths class of this year in this room at this time. Wow. So the particles P, Q and R have masses 0.1, 0.3, 0.6. We've done a few questions like this. I don't think we've done this one, have we? But it's quite a common format. They travel along the same straight line on a smooth horizontal table and have velocities 1.5, 1.1 and 0.8 meters per second respectively. P collides with Q and Q collides with R. Crazy. In the second collision, Q and R coalesce. Ooh. And subsequently move with velocity of 1 meter per second. Find the speed of Q immediately before the second collision. Right, we've been given huge amounts of information, haven't we, in all of this. Let's try and distill some of what we've got. The fact that it is a smooth horizontal table, and it's horizontal and smooth, they're the two words that we use there, that implies that once these things start moving with a velocity, that velocity remains unchanged until they collide with something. We've got no resistance to motion, there's no kind of gravity increasing things as they move down or anything like that. There's no change, no acceleration. They're just going to keep moving. So, we've got the first collision, which is P colliding with Q, and that's what we're going to deal with first. So, if we look at that first collision, we've been doing before and after diagrams with these things. So we've got P and Q, and we're going to deal with the before and after situation of this. Let's move that down a little bit. So before, we had P with a velocity of 1.5 and Q with 1.1. We need to put their mass on here as well. So P was 0.1 kilograms and Q is 0.3. And then after, particles travel along. Right, well we don't know what happens after yet, do we? And actually thinking about this, we'll come back to this diagram, won't we? Because we don't know yet. So we've got a kind of after, should we call it VP and VQ, and that's the first collision, but there's too much unknown in there, isn't there? So we'll come back to that collision in a moment. We've got the second collision which takes place, and actually I think that's the collision that we know more about. So that's the first collision. We've also got the second collision down here, where beforehand we've got Q and R. Q is 0.3. R was given in the question somewhere as being 0.6. We have, that is what we called VQ, the collision of Q, the speed of Q after the first collision. R had a velocity of 0.8. And after the two particles join together with a mass now of 0.9 as they coalesce and a speed of 1 in that direction, with a velocity of 1 in that positive direction. Okay, so actually it turned out that it was the second collision that we knew more about. So if we look at our conservation of momentum equation for the second collision, we've got 0.3 times VQ plus 0.6 times 0.8 is equal to mass, which is 0.9 times velocity of the one coalesced particle at the end, which gives us some stuff, doesn't it? I should have brought a calculator through. Can you borrow your calculator, Jonathan? Okay. So we've got 0.6 times 0.8, which is 0.48, and we're subtracting that from 0.9 to give us 0.42. There's 0.3 VQ. So velocity of Q is that divided by 0.3, which gives us 1.4 meters per second. Okay, that's pretty good going. So we found out that first answer we wanted, and then it said calculate the change in momentum of P in the first collision. Now, in order to do that, we need to go back to our first collision diagram and work out the velocity of P, and then we can calculate the change in momentum. So if we now go back to the part 2, we're doing the first collision using our conservation of momentum equation and saying that we've got 0.1 times 1.5 plus 0.3 times 1.1 is equal to the mass of so we got mass of P times Vp, so 0.1 times Vp plus 0.3 times Vq, and Vq we found as being 1.4. That's where we're using the smooth horizontal table NUS, because it's the fact that although that is the velocity just before the second collision, that means it's the same velocity just after the first collision, because there's no loss of velocity, no horizontal acceleration. Okay, so we can work this out to calculate the velocity. 1 times 1.5 plus 0.3 times 1.1. Take away 0.3 times 1.4 gives us, I think, 0.06 is 0.1 Vp. So Vp is that divided by 0.1, which is of course 0.6. So we had the velocity of P as being 0.6. And so the question said, calculate the change in momentum of particle P. So the change in momentum of P is, well, P has a mass of 0.1, doesn't it? So it is we've got 0.1 times 0.6 minus 0.1 times 1.5. Okay, Matthew, start the video. Giving us a figure of minus 0.09 as our change in momentum. And so what are we going to say here? We have a loss in momentum of 0.09. There's our change in momentum. Okay, and I think they probably accepted either plus or minus 0.09 as the final answer. They did. They were quite happy with either of that. There we go. Is that all right? Of course, we've got an alternative we could have done there, because the change in momentum for P is also the same as the change in momentum for Q. So an alternative approach there could have been to work out the change in momentum for Q, because we also knew all the information we needed. In fact, we could have done it without finding the velocity of P, couldn't we? Because they must be the same, because overall we had a conservation of momentum. But anyway, that's what we got, and there we go. I was supposed to say, and that's maths, at the end of that question. And then once I say that, if you reach over and press the red button on the back,